So the title of the talk today is Microlensing of Gravitational Waves, Prospects and Challenges. Apart from thanking the organizers, I should also thank Akash for pointing out a couple of things which I would like to, which I'll be mentioning in my work as well. Okay, so what is lensing? Specifically, what is strong lensing? So when you have a binary merger, let's say you have a circular binary here that is being merged, you observe gravitational waves from it. And if suppose there is a compact object lying in between the source and the observer, the space-time nearby this object is, it gets deformed because of the presence of the object itself. Therefore, it might sometimes lead to multiple such signals or multiple such GW signals from the same event. So what you are observing is not just a single event, but a copy of one event, but with some phase difference, etc. So this is what is known as a strong gravitational lensing. Now, along with having multiple copies, these different copies are also separated in time, so which we'll call as the time delay between the different images. Now, why is this important? Is because, as we know, that the gravitational wave observatories are being upgraded every now and then, and also with the next generation of detectors, we expect that order of 100,000 events to be detected per year. And of these 100,000 events, a small fraction of them are expected to be lensed. So that would be, let's say, around hundreds of such events. So these events will allow us to probe the space-time of the object or space-time near the lens object. And this is where the microlensing comes in, or the lensing of gravitational waves is important. Okay. Now we recall from our high school physics that if we pass a light, or if we throw a light on an obstacle which has a size equal to or about the wavelength of the incident wave, then we see the diffraction effects. And in case of gravity, for example, similar thing happens. And in this particular case, the size of the obstacle could be mimicked or could be replaced by the lens mass or the time delays between the images. Because this is simply because in the units of g equals to c equals to 1, mass and time and length all scales in the same way. So the size is scale as lens masses or time delays, and the wavelength of the incident wave is now the wavelength of the gravitational wave or inverse frequency of the gravitational waves. So if, however, these time delays are much larger than the inverse frequency of the gravitational waves, which in this particular, in the analogy of light and the obstacle, would mean that the obstacle is large enough for light to see, then the two signals will be resolvable. There is no diffraction effect. Okay, and these signals, as I mentioned earlier, would be separated by some time delays. However, if this time delay between these two images or two signals are comparable or just smaller than the inverse frequency, then we see something else. We see the diffraction effect in the gravitational waves. So the first part of the talk we'll be talking about the prospects of microlensing, and this is based on this work, our recent work with Sumanto, Shashwat, Arif, and Ajit. So what we try to ask is, can we constrain the parameters of the lens? In this particular case, we are introducing a charge in the lens. So let's call this charge capital Q, and we're asking, can we constrain this charge through gravitational wave microlensing? Now you can interpret this capital Q charge as coming from an electromagnetic source, meaning like the electromagnetic charge, or it could come from the modified gravity kind of a theory if it is positive. However, if the capital Q is negative, you could also interpret it as something coming from extra dimensional theories. Okay, so as I mentioned earlier, these waveforms, these are time series waveforms essentially. So now if you look at the frequency series or the frequency component or the counterpart, sort of FFT of those waveforms, they look something like this, where the dashed one is the unlensed one, there is no lens. However, with an introduction of the lens, you see that there are variations in this waveform. So we expect that there should be some signatures of the lens properties on these waveforms, right? And which is what we see. So for example, on the right hand side, we have a positive charge. On the left hand side, we have a negative charge, and on the center, it's a zero charge lens, which is just a Schwarzschild lens. Okay. So how do you actually do the constraint or the parameter inference of such signals? So I'm sure people already know these things, but just to for completion, so these you need for a particular set of parameters theta, you are asking what is the posterior distribution of my parameters given a set of data d, and this is given by the Bayes theorem, where the right hand side is the likelihood and the prior, and it's proportional to the probability of the given parameter theta. So whichever theta parameter you want to you are interested in. So this likelihood is something which will be of our interest essentially. So what we do is, in order to compute the likelihood, what you need is the data itself and the templates which Akash have already mentioned. So in this particular case, we need lensing templates. Let's assume that we have some lens templates. Then what will happen is this data will be compared to each of these templates and we'll compute something called the match. I'm not going into details of how it's done or what is match, but you can think of it as how much of an overlap there is between these two things. And this will give us the likelihood. Okay. Higher the likelihood, better match it is, and vice versa. So if you have very high signal to noise ratio, then this likelihood could be expressed in terms of the signal to noise ratio and the match in such a way. Okay. But this is basically an approximation. It's not the actual Bayesian parameter estimation. And so what we can find is, at the end of it, these are the certain constraints which we have put through microlensing on the charge values. For example, how to read these, I'll tell you. So think of any of these panels. So you have an SNR of 25. On the x-axis, these are different lens masses. What I'm injecting, or the true value of the charge, is this. Let's say this is minus 0.5 is my true value. The spread in the y direction is essentially my spread in the posterior. That is my posterior. Okay, so these are called violin plots. And as you can see, as expected, with the increasing SNR, the posteriors get narrower and narrower, meaning you are getting better and better constraints. So here I'm showing you two results for a true value of minus 0.5 and the true value of minus 0.1. Okay. So here my prior range is in the negative side of the Q, which is basically saying that if the Q is from some modified theory of gravity, or sorry, from some extra dimensions. You can also put certain similar argument and talk about the prior on the positive side of Q. And now here what I'm showing you is a true Q in equals to 0.5, 0.5, and true Q equals to 0.1. And you can clearly see that the constraints have improved a lot in the positive side. So what you expect is that the constraints for positive Qs should be much better than the constraints on the negative Q. Similarly, you can ask, what if the lens does not have any charge at all? So what if the lens is chargeless? That is, when you have a Q equals to 0, the true value of Q equals to 0, these are my posterior distribution. By the way, these lines, horizontal lines, these mark the 90% Gradivan intervals, and so on. Okay. These Y values are the impact parameters. So what are these impact parameters? Suppose you are looking to the lens, it's my line of sight, but the source could be at an offset, right, from the line of sight. And this impact parameter essentially is at that offset. Okay, this completes the first part. The second part is in understanding what are the challenges in this analysis. And this is an ongoing work with Gopal from Ayuka, Arif, and Shashwat. So what we're trying to do is to construct surrogate models for microlensing. These are on the same, on a similar fashion to the work that Akash has mentioned. So the problem with the previous thing that we have mentioned is that we have not done a full Bayesian parameter estimation. We have made an approximation of such. So in order to do a full Bayesian parameter estimation, what you need to do is you need to sample the posterior through certain stochastic sampling techniques, such as Monte Carlo or Markov chain Monte Carlo, or let's say nested sampling or something. So what happens is, in order to do this, you need to evaluate this likelihood at different points. And evaluating my microlensed waveforms takes some time. And this time is large enough to discredit or to disallow us from doing any full parameter estimation. So what we are trying to do is to create accurate as well as faster waveform models for microlensed waveforms, and we're expecting that to be sufficiently fast enough to be able to do full parameter estimation. And additional problems can be following. So if you increase the number of parameters in your lens model or in the full microlens full waveform, then the likelihood evaluation time also becomes exponentially large, because your parameter space will also be, it will be exponentiated in that sense with the number of parameters. So this requires first generation of templates, and so we try out surrogate models for microlensed waveforms. So the idea is very much similar to what has been already talked about, but there are certain differences which I'll not be indicating here, but the idea is same. So you first have a training space in which you expect to create a very accurate model for or lensing waveforms for these microlensed lens models. So given any lens, for example, if you give me a spinning lens, or if you give me a charged lens in this case, or any other lens, I should be able to create a training space. From this training space, what I'll do is I'll create a reduced basis, which is like a slower dimensional variation of the full training space. Then you have the empirical interpolant. It's the same as what Akash has mentioned. These two things combined is what is known as my greedy data. Okay. Once I have this, then I perform a fit in the parameter estimation, and finally evaluate the model at any parameter value. So the point to note is that the whole part here, this is time consuming. Okay, but this part is done offline, so you don't have to do it at the time when you are running the parameter estimation. The only thing that you want to be fast enough is this part, evaluating the parameter at the final stage. And addressing one of these questions that I think Harshit asked about these errors, how do they go with the greedy parameters? So here I'm showing you one of these error plots. This is an error on the reduced basis errors, not the interpolant errors, but the reduced basis error. So as you can see, with the increasing number of greedy parameters, you expect it to go down. And so I'll just take 1 minute, go down, and this is kind of a validation for your model. Here, what I'm showing you are the results for a charged lens for the same model, but now you have a gain in the computation time of at max of the order of, let's say, 600 or so, which gives you approximately of 1 millisecond or something. The time taken to evaluate each of these models is about 1 milliseconds. Same with the accuracy. You can see the accuracy is 5% or even lesser than that. So okay, so this concludes my talk. So upcoming observations, we expect them to detect a number of lensed gravitational waves. With these different lensing observations, we can potentially probe the nature of the lens. It could be a black hole, it could be some black holes with hairs, could be exotic compact objects, etc., and put constraints on these lens parameters. Bayesian parameter inference for these lensed signals requires faster likelihood evaluation. So what we do is we implement a surrogate model based on the greedy algorithm for accurate and faster evaluation of microlensed waveforms. That's it. Thank you.
Questions? Yeah, Adit.
Yeah.
With different impact parameters?
Corner plots or
in the first project that you were showing some, it's not corner, violin plots. Yeah. Why is it that higher impact parameter are well constrained than the lower ones?
That's a good point. So because these are to do with the morphology of the time delay surface itself. I'm not going into the details of it, but how we construct these is by going to the IFFT domain in the time domain and construct the lensed amplification factor. And if you look at the morphologies there, so for higher impact parameters, so if you look at for these cases, for example, these higher impact parameters have very large deviations in these morphologies, in the time delay morphologies, as compared to the lower impact parameters. And so they are constrained much better. But this also has to do with the frequency range that you are dealing with, you are talking about. Suppose you go to a different frequency range, you will probably see a different scenario. So here what we are doing is for I think it was for O5 based data, PSD.
Can I follow up? Okay. Can I follow up? One more question or? Huh? Okay.
Okay. Yeah. So my question is also related to the first part of your talk, where you talk about these charged black holes and so on. So my understanding was that in astrophysical context, mostly these charges get either shorted out or screened very rapidly. So then, what sort of realistic astrophysical objects can this be applied to?
So first of all, this would give you an independent way of measuring the charge. So for example, the kind of black holes that you are looking at currently, so you do not expect them to have astrophysical charge, for example, yes, but this would be an independent measure of those charges. Second of all, this also would lead you or enable you to understand the different gravity theories, which also include the scalar charge, not just the electromagnetic charge, for example. As I mentioned, for if you have a positive Q, it doesn't have to come only from the electromagnetic charge. It could be also from a modified theory of gravity.
Sure, but that would also be, I mean, I would assume that would also be shorted out by surrounding medium electromagnetic charge, right? Like, why would that charge stay?
But that is not an electromagnetic charge, right? So why should we get dissipated away?
So I don't know more about modified theories of gravity, but does that modified theory gravity charge do not interact with charged particles in the normal
I'm not sure, but if you yeah.
Okay, we
Ashik
will have
comment on
next
this.
talk now. Yeah, we can discuss this later. Thanks, Uddeepta.